My name is John Thomas. I'm calling in from MStar Simulations. Today we'll be speaking about real-time CFD-based bioreactor models with integrated process control. So we're going to be talking a bit about transport physics. We're going to talk about interfacial mass transfer. We're going to talk about blending, and we're going to talk about PID control and biomass and metabolites and all sorts of fun things. I'm going to make sure this talk is recorded and transcribed. What that means is that you'll be able to not only follow up after the fact as you read along, or watch again should there be any questions after the fact. But with that, let's go ahead and get started because I think we've got a decent quorum. Okay, let me go ahead and see everything in all its glory. It's September 4th where I am. It may not be September 4th where you are, but welcome to the presentation today. Let me go ahead and kind of get my slides organized here and make sure they're good to go. Okay. Webinar agenda today, we're talking about bioreactors and digital twins thereof. And I'm particularly speaking to a paper I published last year with Bristol Myers Squibb on bioreactor scale-up, bioreactor optimization, and bioreactor design. And so everything I'm speaking of today was addressed in this paper, as well as a more recent paper with Pfizer that I can send on a case-by-case basis. But I'll be talking about what goes into bioreactor and how we attempt to model it. And also I'll be talking about the idea of a digital twin. I'll be talking about the physics and feedback control. By that I mean the PID control systems that govern bioreactor performance. Now we can integrate those physics into a CFD simulation to model the coupled effect, I should say, of CFD, of simulations, and of process dynamics, as it were. I noticed someone just made a chat. I can't see the chat unless I step away. And so I'll do my best here to see what we got going on. So I can monitor if there's any sort of pressing questions or not. But to be sure, please share questions. Please send them in the chat, and I'll speak to them on a case-by-case basis at the end of the call. But yes, 안녕하세요. Oh, thank you. Hello to you too. Someone, Ju Chong Hwan, said 안녕하세요. And yes, 안녕하세요. 제 이름은 John. 옛날에 제가 한국에 샀어요. 옛날에 제가 한국어 잘했어요. 이제는 다 잊어버렸어요. But long ago I spoke Korean, and I can still read it. But either way, I'll talk a bit about building the twin, some of the key physics, as it were, and then I'll talk about applications and next steps. So I think we've delayed enough. Let's get into the agenda. At MStar, we are strongly focused, and this will motivate much of what I'm going to be speaking today, is on GPU-based simulations, okay? All simulations that we'll be running today are designed and tailored to run in GPU environments. And I'm making this the most important point and the starting point because this is what makes all the simulations possible. I'm going to be showing you things today in terms of modeling time-dependent three-dimensional flow fields over very large timescales in practical, over many days of simulated processes in a very short simulation timescale that is using fast-running simulations. And what's making this possible, again, is our GPUs. GPU stands for graphics processing units, as it were. They are very compute dense. Said again, a GPU tends to have tens of thousands of cores. In contrast to a CPU, it might just have 4 or 8. GPUs have memory on the card. So the memory the GPU needs is on the card. That makes the memory bandwidth very high. And the net effect is that one good GPU can typically do math, 30 times faster than one good CPU. Likewise, one good GPU can shuffle memory back and forth 30 times faster than one good CPU can with memory on the piece on the memory on the motherboard. So one good GPU can typically do the same amount of science or same amount of calculations as several hundred CPUs. And this is an important point because we're writing code that's designed to run on GPUs. As a consequence, MStar simulations typically run hundreds of times faster than conventional finite volume codes for CPUs because we're using GPU native algorithms and GPU architectures that allow us to run very quickly compared to conventional approaches. Now, what this allows us to do is track more physics explicitly. That is, instead of just running the same old simulations 500 times faster, We're instead changing the amount of physics we can put into simulation and the types of disparate behaviors we can combine into one simulation. And I'll give you a roadmap about how this works. As engineers and scientists, we have two extrema. At the coarsest level, we have correlations. These are not very calculation or computer intense, but they just link some engineering output to some engineering input. These correlations are not specific. They tend to be the correlations are not general. They tend to be very specific to a given system. And likewise, they mask a lot of the physics, but nonetheless, they're not very compute intensive and very simple to use. At the other end of the spectrum, we have things like the wave equation and the Schrodinger equation. These things are general. They can solve any system, but the problem is they're phenomenally complex and they're not practical to solve for engineering systems. It's between these two that we're operating today. We have continuum representations. This would be like, a finite volume method or whatnot. Then we have carrier, mesoscopic based approaches, where we're describing the net effect of these continuum behaviors in terms of the underlying mesoscopic transport carriers. Now, importantly, the lower we go on this train, the more physics we're resolving explicitly, and the fewer assumptions we're required to inject into our model. So again, a correlation has tons of assumptions. It makes assumptions about the system setup, about what the Reynolds number is, the fluid operating regimes, and correlations often have limits on when they're applicable. Wave equations have no assumptions. We're just assuming that Schrodinger's equation is true and a wave function is valid. And the closer we get down here, the more general, our simulations become, the less tied they are to one specific system, and that's where we want to operate. Because instead of spending all our time making one correlation good for one system, we spend our time making generalized modeling approaches that can be applied to a very wide variety of systems that make our modeling efforts more useful. Here's an example of that in action. In this particular MSTAR simulation, I'm doing CFD-DEM. I'm modeling fluid flow with a free surface, and I have particles as well, and the particles have contact mechanics preventing them from collapsing. As time goes on, the agitation of the impeller causes these solid particles to become suspended. Importantly, I have a PID controller embedded in the model that is dynamically adjusting the impeller speed to achieve a target suspension ratio. And this is neat because it's not just a RAND simulation where I'm looking at a snapshot of the flow field. It's not just a DEM simulation where I'm looking at only particle settling, nor is it just a short, brief interval of watching fluid and particles move together. I'm modeling minutes of flow field with inline control, looking at multi-phase simulations and modeling the entire process. So this is what I mean by getting closer and closer and closer down to the transport carrier level description. We're modeling time-accurate, three-dimensional physics. We're modeling multi-phase systems, and we're doing this in real time, as it were. So rather than looking at snapshots or using generalized or system-specific correlations, we're able to put more physics in the model to make them more generally useful and applicable to a wider variety of systems. That is, if we change the density of these particles, or we change the size of the vessel, or the type of impeller, as it were, we would run the same system. We wouldn't need to recalibrate a correlation, redevelop a correlation, or make significant changes to the continuum model. All these physics are captured explicitly would allow us to use this model, the same model, for a wider variety of systems. So this kind of pervades how we approach simulation. When we're modeling fluid flow, we are solving DNS and LES simulations. We're not doing RANs, we're not doing time average results, we're actually capturing as much of the turbulent energy spectrum as we can explicitly, and we're doing this in 3D space and time. So here's the time evolution of the flow field in a lab space, which is being vented due to a chemical leak event, where there was some sort of sensor that detected an abnormal concentration, and the vents need to turn on to see how long it would take to purge the room. When we're doing particle transport, we try to model every particle. And here's an example of a dissolution problem, where we have a large number of particles that are dissolving as they're agitated by this anchor impeller, and that's changing both the size of the particles and the corresponding viscosity of the fluid. Now, we may need to use some partial methods if the particle count gets too high, but importantly, we're describing the nature of these particles in their true form as particles. We're not using some looser representation or continuum representation. We're trying to describe the behavior, the physics in terms of the actual constitutive behavior. Likewise, for species transport, we are using some sort of course, a finite volume-based approach to describe the evolution of species, but we're doing explicit coupling to the solids. We're doing explicit coupling to the bubbles. Yes, we may need to inject some boundary layer theory if our grid resolution is too coarse to resolve the physics near the wall or near the bubble, but importantly, we're tracking as much of the species transport, advection, diffusion, reactions, etc., explicitly and in tandem with the other ongoing physics. For conduction as well, say conduction through a solid body or whatnot, we're doing transient conduction with a full 3D solution. Yes, we may use a 2D approximation if necessary, but importantly, in every approach, we're trying to attack as much physics as possible. And when you can run on GPUs and make these simulations run this fast, this type of mechanistic-based approach becomes practical. So again, this will not be practical when running on CPUs, right? But this becomes immediately attractive when running in GPUs that make these simulations industrially relevant. And everything I'm showing here, this is maybe a couple hours of runtime on a laptop. And that's what I'm talking about, the speed improvement that comes from GPUs. So we're talking today about bioreactors in particular. And I wanted to emphasize, the scope of physics we're trying to interrogate in these models and how useful this can be. So when we think about a bioreactor, we have a wide range of operating conditions and physics going on inside this vessel. And what we're going to try to do here, because these models can run so fast, is develop first principles models that tie all these things together. I'll explain it like this. For most operators, they can control things like a DO set point, an impeller speed, a fluid volume, a pH set point, and some sort of feeding profile, like what sort of glucose and glutamine they're adding. And these control variables ultimately inform like cell growth or titer yield. Like eventually all of these physics inform what we're getting, but the means by which they inform cell growth and titer yield is somewhat complex and informed by a variety of physics. The DO set, for example, these parameters underneath the hood are informing some sort of controller configuration, right? Some DO controller that's informing a microsparge, some pH controller that's informing CO2 or some sort of base solution. The reactor configuration also informs how these operating conditions and controller configurations inform process outcomes. Said again, the impeller geometry and impeller speed inform the energy dissipation rate. The sparger configuration and the flow rate inform the KLA, which is informed by the EDR, which again is informed by impeller speed and geometry. These KLA values inform the DO levels, which inform the controller's response, which informs OUR, of course. These CO2 flow rates inform the time evolution of the pH, which informs the carbon dioxide evolution rate and the cell growth. And so we have all these kind of links between operating conditions, controller configurations, reactor configurations, and process outcomes. And then historically, we've looked at individual boxes. We've used simulation to look at, say, just the EDR around the impeller. Or we've used simulation to look at maybe some sort of estimate on KLA. Or we used CFD simulation to look at maybe the relation between impeller speed and impeller geometry and EDR. What we can do now, though, with these more modern approaches is look at the holistic picture of all these processes and see directly in the simulation how changing the fluid volume and the DO set point inform cell growth directly in the simulation by capturing these physics explicitly. So we're going to be considering a few different systems today. I'm going to be considering the Amber 250, which is just a lab scale system, and I'll be considering the Accelerex XDR 1000 and 2000. These are both single-use bioreactors agitated by a single impeller. The Amber 250 has two impellers, and it has a simpler sparge, which is dip tube, whereas these larger scale systems have a microsparge that produces small bubbles that are injected in the system immediately below the impeller. All three systems are going to have probes that characterize the time evolution of the local dissolved oxygen concentration and the pH. And we will be using these probes to inform how we're going to add oxygen and feed to the systems. In terms of scale, the Amber 250 system you can fit in your hand. The 1000 liter system has a diameter of about a meter, as it were, and the 2000 liter system is about 1.2 meters in diameter, to give you some idea of scale. These are typically filled, the 1000, 2000 are typically have bags inside them, which make them disposable. But we're going to assume that the bag is well in contact with the vessel wall, such that we have the shape here. We're not going to be looking at the effects of the bag deformation. We could, but we're not for our simulations today. In all of these systems, we're going to be considering PID control. And this is an important point because the behavior of a reactor is strongly correlated to the behavior of the control logic, right? And these control logic events inform what the system does in response to excursions. For example, when the system measures that the DO at the DO probe is below the target value, it's going to adjust the gas flow rate. And how it chooses to do that is a function of the PID controller logic and the PID parameterization. So we want to be, if we're going to accurately model how the system is going to respond, we need to include this logic in the CFD model explicitly. Said again, as time goes on, we need to be able to predict how the system is going to add oxygen in response to oxygen deficits. And the fact that we can model these physics explicitly inside the code gives us more insights into how we can optimize this system. Said again, we're not just looking at oxygen dead zones inside the vessel. We're not just looking at a PID controller. Within the context of MSTAR, we're able to couple these physics together to see how the dead zones inform the PID and how the PID response time ultimately informs the evolution of those dead zones. And that's very compelling. We can do this for pH. We can do this for glucose or the nutrients. For example, a glucose probe might be measuring the inline glucose nutrient concentration. And from any deficits from a target value, as it were, that might inform how glucose is added to the system as well as other nutrients. And again, the same logic applies here. In many simulations, maybe we'll look at a glucose blending time, or maybe we'll look at how glucose blending competes with glucose uptake. But we don't typically model how the controller logic informs the addition and evolution of glucose concentration, because the controller logic takes hours to operate, but simulations typically only model, say, tens of seconds or minutes of blend time. With MSTAR and GPUs, we can model hours of process mechanics and see the combined effect of glucose addition, the bioreactions, glucose probe measurements, and the effect that has on system outcome. So importantly, we're integrating process control into the simulation. What that allows us to do is take a broader view of our system and understand not only what the physics inside the vessel are doing, but what the controllers are doing and how they're feeding off of each other to inform the aggregate system response. And again, this is made possible again by GPU-based algorithms running in GPU-based environments. So again, just as I said before, when we're modeling fluid flow, we're solving the Navier-Stokes equations, but we're using the Lattice-Boltzmann method to attack them. Lattice-Boltzmann is phenomenally efficient in GPU environments, which is why we do it. So here we're modeling the transient three-dimensional flow field. We're seeing the velocity of the impeller. We're seeing the eddies discharge through the vessel. And we're seeing that macroscopic flow field evolve throughout the system. Now this is cool in of itself, and this simulation is noteworthy that I'm able to model, minutes of process mechanics routinely on the laptop. And I'll go ahead and start this again to illustrate. On the left is a velocity field, and the right is a blending. So I've added glucose to the top of the vessel here, and I'm watching this glucose evolve throughout the vessel to see, again, a blend time and distribution of that glucose as it interacts with the biomass. And again, these simulations on their own are interesting, but this is just the start. That is the transient three-dimensional flow field and watching the evolution of the species on top of it. We're just getting started. Because these things are so easy, we can start to layer on much more complex physics, inclusive of the three-dimensional reaction kinetics, as well as explicitly resolved mass transfer. I mentioned we're using Navier-Stokes to solve the advection diffusion equation for the scalar, for the fluid field and velocity field. We're using advection diffusion reaction to predict the time evolution of the scalar field. Said again, what's informing the evolution of this glucose is the underlying velocity field, diffusion obviously, as well as in the underlying reactions. When we have oxygen transfer, we're going to be modeling oxygen transfer on a bubble by bubble basis, using the bubble specific KL, the bubble surface area, and the driving potential. And so importantly, we're modeling physics at the level of the individual transport carriers, and we're solving them in tandem and in real time, which means that changes in the viscosity due to the changes in the glucose concentration do inform the time evolution of the Navier-Stokes equations and the resultant velocity field. Bubbles, again, as I mentioned, are modeled explicitly. We've published about this a lot with a number of pharmaceutical companies. Both Pfizer and BMS are recent papers that we've spoken about KLA and breakout mechanics. Importantly, as I mentioned to begin, we're taking a very mechanistic approach. We're not using a population balance model. We're not using some sort of empirical correlation. We are modeling every bubble as it comes in the bioreactor. We are modeling every bubble as it undergoes breakup events. We're modeling every bubble as they participate in possible coalescence or bounce events. And when we use these bubble level approaches, we have a very generalized modeling approach that doesn't need to be changed between different operating scales or operating conditions. Said again, inasmuch as our breakup mechanics rules, and they talked about in depth in our literature, appeal to first principles relationships such as EDR, informing bubble breakup, or appeal to first principles coalescence relationships, they don't change between scale or operating condition. All the changes in vessel type, vessel scale, impeller speed, etc., the net effect of those changes on things like EDR and coalescence mechanics are folded in organically to the model. It's practical to model tens of millions of individual bubbles. Above that, we may use a parcel-based approach, but for most bioreactors, even big ones up to 10,000 liters, we can generally use these explicit approaches to model mass transfer and the multi-phase flows. So we've talked about this a lot in the literature. We've validated it quite rigorously. And importantly, we've shown that it's general across scales and operating conditions. So we'll be using that today. So, and importantly, we validated this kind of PID CFD in previous systems as well. This is very compelling, and I want to show you how we validated this against measured data from Bristol Myers Squibb. In this particular test, they wanted to understand how changing things like the impeller speed and the DO set point changed the response of the system. For example, after 10 minutes, there was a change in the impeller speed from 115 to 150 RPM. What did that do? Well, according to the measured data, there was a spike in dissolved oxygen concentration levels, and then eventually, after about 30 minutes, returned to the target value of 40%. What drove that spike? Well, the higher impeller speed cut the bubbles up more effectively, increased KLA, thereby increasing oxygen transfer to the system. The PID controller responded by decreasing the gas flow. That is, the higher impeller speed made better use of the gas bubbles, which meant the system needed less gas to achieve the target DO level. That's how the PID system responded, and it took about 30 minutes again for the system to recover the target DO in response to the step change in impeller speed, step increase in impeller speed. After about 42 minutes, they changed the DO set point. They went from 40% to 60%, keeping the impeller speed constant. How did the system respond? Well, suddenly we were below the target value, and so the system shown in black gradually increased the gas flow rate until it was able to achieve the target DO level. Said again, to realize that higher 60% set point, the system, the physical system in the lab, the PID controllers, increased the gas flow rate, and it took about 10 to 15 minutes for the system to recover. This is valuable data for the process design engineers, so they can understand what the recovery times might be to excursions. One last test, they dropped the impeller speed back down to 115, keeping the set point at 60%. What did the system do? Well, immediately, because the impeller speed went down, it wasn't getting enough mass transfer. There wasn't enough bubble breakup. There wasn't enough surface area, as it were, that allowed the KLA to match the oxygen, the set point demands. And so oxygen levels went down. They went down dramatically because the O2 flow rate was too low to supply the system with an appropriate amount of oxygen given the cell's consumption rate. How did the system respond? It gradually increased the gas flow rate until the actual DO level matched the target value after about 30 minutes. Now, importantly, the black data here was always measured experimentally. And with no parameter tuning and no adjustment between runs, the blue is exactly what the simulation did. Okay, look what we're getting right. We're able to predict the recovery times of the system in response to step changes in DO set point and impeller speed. We're able to predict the excursions from target set point value. And to within about 10%, we're able to even predict what sort of gas flow rates the system is going to need to achieve the target set point values. Now, importantly, nothing was changed. This was one simulation. We didn't change rules over the simulation. We didn't mess around with numbers to get it to work. Because we're appealing the first principles and generalized momentum, species, and bubble transport models, nothing changes between run and scales. And the fact that we're getting it right tells us both our fluid mechanics and our control dynamics are right. Now, importantly, this was the validation against what was measured versus simulated. And I think it's really cool to see the code absolutely nail that predicted that measured response from first principles using only generalized transport models and the appropriate PID parameterization, that which is used in the lab. So that's how we know these things are right. And in fact, the simulation can show us things that are hard to see experimentally. Look at this here. I'm going to show 3 or 4 zones here. 1, 2, 3, and 4. These correspond to 4 different operating conditions. At operating condition 1, we have impeller speed of 115, DO set point at 40. What the system tells us is that the probe is indeed achieving the target value. What the experimental system doesn't tell us is that we have a dead zone in a region that's not being measured. Set again near the center of the vessel, the DO levels are only at 20%. So although the system is behaving well and the PID controller in the experiment and the simulation is working correctly, the simulation shows to us that this controller may not achieve target output. Said again, this particular probe is, yes, achieving its target value at the probe location, and the PID controller is doing a good job on what it's told, but what it doesn't know is that we have DO dead points. The simulations pick that up, and more importantly, show us how to fix it. For example, here's operating condition 2. We have a higher impeller speed at that same target set point. And immediately we see in the simulation that yes, the probe is achieving the target value, but more importantly, we're achieving homogenization throughout the vessel. That is, we only have an RSD of maybe 6.8% as opposed to 12% lower impeller speed. So as an operator, this gives me guidance as I can quantify, as it were, what my DO gradients will be across my vessel and how those will be informed by my operating conditions in a way that experiment alone won't show me. That is, I can match what experiment will give me, and then beyond that, show what the experiment can't. Likewise, at this higher target speed here, we see that we achieve our target value. And to some extent, we have better homogenization at this higher impeller speed. Once we drop down to 115 again in terms of impeller speed, even at the higher set point, we instead see a 20% variation in DO levels, okay, across this vessel due to the choice of operating condition. And this is very compelling to our biopharmaceutical operators because, yes, we can confirm that the code is right by looking at the steady state response and the response of the probe as step changes. And beyond that, we can show them the user what their probe can't see. And that is gradients across the system and the deleterious effects those DO gradients might have on overall cell growth kinetics. So this is a very important validation as well as application of the code. We publish this in the open literature. You're welcome to read it, or you can contact me directly for the manuscript if you want to talk about it in more detail. I'm also happy to send out the actual MSTAR models that we use to develop these codes, as it were, because foundationally, they're pretty easy to use, as it were, and they're not particularly challenging. I'll call these up. We can step through them later should we want to. These particular models. Okay, now we can even go further because what these models are very good at is showing things like oxygen control. We can do the same thing for pH control, look at pH variations. Those are all discussed in the literature. We can go further. We can even integrate all of the cell growth kinetics to see how the DO gradients, the feeding profiles, and the agitation inform titer and cell growth. So foundationally, these should be familiar to most people. Here's our time evolution of our cell density as a function of growth and death rate. And here are the 4 metabolites we're considering. We have glucose and glutamine. Those are both part of the feed, okay? they're going to be in their time evolution will be informed by some conversion factor here, some maintenance coefficient, as well as the biomass concentration, which is gobbling the glucose and glutamine up. But again, we're going to be adding glucose and glutamine to the system in response to the consumption by the biomass. Lactate and ammonia are not added to the system explicitly. They're products of the cell growth process. Lactate and ammonia are byproducts, I should say, and they have a deleterious effect on cell growth. Said again, as lactate and ammonia levels go up, that increases the cell death rate, okay? And so foundationally, we want to keep an eye on lactate and ammonia growth and see how we can trade those off in a way that maximizes cell density and titer growth. And here are typical evolutions. This is from the literature, looking at cell density, looking at glucose, and this was a target glucose value they were achieving to maximize growth, glutamine levels, ammonia, and lactate. Here you can again see ammonia growing during the growth phase, relatively constant during the maintenance phase, but lactate tends to grow throughout. These guys are, glucose and glutamine are our degrees of freedom. Ammonia and lactate are the things we're trying to manage, and manage in a way that maximizes cell density and maximizes titer production. These reactions are typically measured on the order of days, okay? So we have a large range of length scales in our system, but we can handle that. So here is, again, some modifications we're making to this code. We're going to be adding on to those equations a glucose feed and a glutamine feed. So QF is the time evolution of the nutrient feed rate, and the concentration of glucose and the concentration of glutamine are the concentration of those species in the feed. Again, lactate and ammonia don't have a feed. They're not being produced or added, they're not being added externally. They're being produced directly by the metabolism. We also have oxygen, of course, and the OUR tends to go up with increasing biomass. This admittedly is a semi-empirical relationship. This relationship between OUR and, the DL rate and the OUR. But foundationally, it's grounded in some measured data we have. And here we can see the sensitivity of the cell growth to these feeding characteristics. So for example, if I take my glutamine, as it were, and I have my glucose, a fixed glutamine level and different glucose levels, I can see, for example, that if my glutamine level is is too high, I'm going to underproduce in my cell production. If my glutamine level is too low, I'll get a lot of growth, but then I'll die quickly during maintenance phase. If my glutamine concentration is just right, I get good growth and good maintenance at the end of the 14-day period. These inform lactate and ammonia production as well. If I have too much glutamine, I produce too much ammonia, and that ammonia leads to reduced cell density. If I have too little glutamine, I get too much lactate, which again leads to death during the maintenance period. So understanding how we can maintain glucose and glutamine are crucial, because this has, again, 10, 20, 30% effects on titer production and cell density, which can make an incredible amount of value to a commercial production line, as it were. Now, one important point that goes into the numerics, as we're solving these systems, we're operating over a very long time scale with slow kinetics. So in order to make these reactions tractable and practical on the computer, we need two considerations. First, and I'm being a bit technical here, but we non-dimensionalize. This is not a problem. Non-dimensionalization is routine with these simulations, but it's necessary because we're going to be modeling a system with an impeller moving dynamically, with bubbles moving dynamically, a time step on the order of, maybe a millisecond or less. We're going to have very slow reactions that take days to complete. So in order for us to be able to handle that disparity in just machine precision, we're operating with dimensionless values. This is a pretty specific point, and I'm happy to address it in more detail should folks want to have a sidebar discussion at a future date. Likewise, we're also going to think about reaction time scaling. Said again, we've got a simulation time step on the order of 10 to the minus 3 seconds. Our bubble breakup time is on the order of hundredths of a second, maybe 0.01, 0.005. Our eddy lifetime is an impeller RPM is on the order of 1 second. Our bubble residence time is 10 seconds. Our blend time is maybe 50 seconds. Our PID controller is tens of seconds, as it were. Our reaction time scales are millions of seconds. And so one thing we can do to improve process efficiency with very little loss of generality is to accelerate these reactions. That is, take a 14-day process and assume that it only takes 3 days to complete. So that again, we can add some time scaling that allows us to avoid, we can do it. We can model 14 days if we want to. But if we instead accelerate those cell growth kinetics to occur over, say, 2 days instead of 10, it's still fully decoupled from the PID controller timescales. These reactions are still infinitely long compared to all of the physics, but it makes simulation much more tractable. So I'll be demonstrating how this is valid, and I'll be using this though throughout our results in an effort to make these simulations a bit more efficient. That is, simulate a few days as opposed to 14. Importantly, we can do the full 14, that's not the problem, but if we can get the same insights over a 3-day process that's accelerated in the simulation, that saves our simulation run times by a factor of 4, which is something I'd like to do. So let's go ahead here and watch this full system behave. So here I've got, this is moving very, very fast, so I apologize for the movie, but I have local DO on the left. So let's focus on this left picture first. As the biomass grows, its DO demand is going up. And we can see as the DO demand, as the viable cell density is going up, it's demanding more and more and more and more oxygen. The PID controller is responding by increasing the gas flow rate. But look at this. When our oxygen transfer rate is maximized, here again we see those dead zones. Dead zones are notorious in these single-use bioreactors. But importantly, we can see the formation of that dead zone, the persistence of the dead zone, and how that dead zone ultimately informs cell growth. And we can also see how the PID parameterization informs the dead zone. So again, here is the time of evolution of the DO field in response to the oxygen demands, the changing in the gas flow rate due to the PID controller that's modeled in line with the cell growth kinetics and this operating vessel. Let's go ahead and take a look at this glucose now. So the glucose is what's being fed into the system. We're doing something similar to a constant feed. So as time goes on and cells start to grow, their glucose demands go up. So we're adding more and more glucose to the system in an effort to keep these cells fed and keep the realized glucose value at its target target condition. And here we can see this competition between addition and consumption. We're adding this glucose in, its blend is being gobbled up, but we're doing a pretty good job throughout time of achieving our target value. But nonetheless, we can see how these glucose variations are persistent throughout the system and how that does inform the response to the PID. And again, this is through a continuous feed of the glucose. As it would go below the target value, the PID controller would call for more glucose, and that's what leads to these periodic pulses in the system as it's adding glucose to achieve the target value again, which was maintained throughout the simulation. Let's take a look at the combined effects of the local DO percent, the glucose concentration, and the viable cell density. Now, these viable cell density reactions are very slow. And so we're not going to see spatial variations in VCD growth. We're instead going to see a pretty consistent viable cell density that's evolving over this multi-day process. Now, this is monotonic. We're going from low values to up to around 5 or so as our cell density reaches its maintenance value. So we're not seeing variations in VCD, but the target value we achieve is a function of the DO variations and the glucose variations. Said again, although there aren't strong spatial variations in the viable cell density, we do achieve a target value. The target value we achieve is a function of these underlying feeding profiles, target concentrations, and DO PID control. We can look at these on a case-by-case basis as well. VCD growth, very similar. And this is kind of cool. On the red is what we would predict, as it were, using the empirical correlation in literature. The black is what is measured using those from literature. The red is what we're getting out of the code, okay? And to be able to achieve those target glucose concentrations and those target cell densities is very encouraging. Likewise, for the glucose control, now let me go back here and play this movie. Sorry about that. We can see how this is our target value shown in black, And the red, that's what the controller is achieving. That's what it's trying to achieve. This is the response. This was the flow rate put into the vessel over time that was required to achieve this target glucose concentration. So we're able to see here is how we might optimize the controller in a way that maximizes that minimizes the difference between the realized and target glucose levels, and more importantly, what that controller is going to do. What is maximum flow rate going to be? What kind of pump we're going to need? What sort of response times and PID parameterizations we need? So we can use the simulation to tune and optimize the PID. We can use the simulation to optimize the feeding profile. We use the simulation to see how suboptimal PID parameters ultimately inform cell growth. That's what I mean by this holistic type of modeling. We have all the connections between operator topology, the system set points, PID parameterization, vessel topology, and cell growth kinetics. And we would put those all in one model. It allows us to see directly how we optimize system performance. We can do this across scale. And this is an important point. Because we're using generalized first principles models, LES simulation, mechanistic bubble breakup and coalescence, explicit breakup models, explicit coalescence kinetics, none of these physics change between scale. Whether we're doing the 250, whether we're doing the 1000, whether we're doing the 2000, we can use the same model over and over and over again, changing only the vessel topology and scale. Nothing else changes. And that's the power of running a model that is based on more foundational physics, is we develop the framework and then rinse and repeat each particular scale, as opposed to making a new model every time for each scale. And important for this system, we can see how going from lab scale to pilot scale to production scale informs the PID response, informs the cell growth, informs the glucose levels, informs the cell density, informs the titer production. We can use one model to interrogate every scale. So if we're looking to scale up, this is how we do it. We have these generalized approaches that allow us to see not only what the system is going to do in response to the PID loop, but how those physics are introducing spatial variations within the vessel, and how those variations are informing final cell density. And again, I made this point earlier, but I'll speak to it more directly. We can use these models to actually develop a controller logic, right? And if you're working in biopharmaceuticals, you know how valuable this is. You know that a poorly parameterized PID controller will yield oscillations, will be slow to respond, will have a lag as it were in response to changes. As opposed to going through commercial batches and trying to optimize those parameters in the field, we can do it completely in silico and go back to the vessel and say, this is your gain, this is your reset, and this will be your response. And not only can we predict the final viable cell density, we can predict what those PID parameters will do for both DO, pH, nutrients, etc., and develop and optimize the process without going through several batches of actual commercial product. I'm going to end with a few conclusions here, show the model, and then open the floor for questions. First, yeah, we can model the standard stuff. That's easy. Fluid flow, species blending, two-phase flow, interfacial mass transfer. That's standard simulations. But what makes MSAR so unique, particularly running these GPU environments, is to be able to extend these simulations to include auxiliary control systems and multi-day reaction kinetics. We talked about oxygen control, nutrient feeding, and it didn't show it here, the pH, but that's in the paper. But because we can run these simulations so fast, instead of being able to run just 2 minutes of a blending process, we can model 2,000 minutes, as it were, of an entire PID control loop, right? Instead of just looking at, say, how glucose blends, we look at how the glucose is blending, how the PID is informing it, and how that glucose blending process, in tandem with the explicitly modeled reaction kinetics, is informing cell growth and titer production. And that's the point. As I go back to this earlier model, let me just go back to this frame because I do want to reemphasize this point, is that we can couple all these physics into one simulation. So as opposed to looking at piecemeal one particular physics, we're trying to interpolate what that EDR will do to DO concentration. We can model it all holistically and they can get a complete aggregate picture of how the system is going to respond. Let me go ahead and jump down here back to my frame. Sorry for jumping around, but I did want to make that slide. This fully coupled model can be used to optimize feeding schedules as well as simplify scale-up campaigns. Again, we're not changing the physics between runs because the physics we're appeal to first principles. And again, we have a mechanistic roadmap here. It's not a dark art. It's not a black box. We can see exactly why this set of operating conditions, why this controller logic, why it made this particular cell line grow in this manner. And we have that kind of holistic understanding. It becomes a very efficient process to optimize systems across scale, to optimize processes across site, and to optimize operating conditions for process yield. I'm going to jump over to the model here to show you a bit more about what this looks like for those who may have MSTAR in their wheelhouse. These models are not particularly complicated. So in this particular system here, I have my vessel wall, I have an impeller, and I have a sparge. My sparge flow rate is set to some O2 sparge flow rate, which comes out of a PID controller. So again, I've got a PID controller that's measuring the probe DO, comparing to a target DO, with the associated gain and reset time informing the flow rate. So we're modeling this stuff directly, guys. Likewise, for the glucose PID, we've got a target value, we've got controller parameters, as it were, and then we're using that target glucose feed rate to inform how glutamine and glucose are added to the system, as it were. We have cell growth reactions, and these are familiar to you. But if you look at this here, you'll see these are, look at mu growth, mu death, conversion ratio, etc. for glucose, glutamine, BCD. These reaction kinetics here, guys, these are exactly what I showed before. That's these guys right here. We're modeling them explicitly. If I go even deeper to look at things like the viscosity, here my viscosity is a function of cell density. So we have all these physics coupled together on model that allows us to interrogate them in real time. What are the inputs? Physical properties, concentration, solubilities. We have cell growth kinetics. These are the maintenance coefficients and conversion factors, as it were. We have initial conditions that describe what my initial glucose, glutamine, viable cell density might be. But these are the physics that go in. So whether this is 1,000 liter, 20 liter, 250 milliliters, as it were, whether it's a 10,000 liter vessel, these physics don't change. Yes, the PID controller might change. Yes, the wall and the impeller topology might change. But because I have these physics wired up, they're good to go. So if I go ahead and run this guy, as it were, I can begin to see how this goes. Let me go ahead and kick this guy off and let it run. I can watch this process evolve in real time. And that's the point of the simulation, guys, is to get a holistic, three-dimensional view of a process across space, time, with process control. I'll go back to my closing slide and open the floor to any questions. Folks, thank you so much for joining us. Thank you for taking time out of your day to kind of attend this lecture and see how we're attacking these questions. I am happy to share if you're an MSTAR user, I'm happy to share any of these models with you, as well as the papers we've written with Pfizer and Bristol Myers Squibb that show these things in action. If you're not an MSTAR user, give us a call, okay? There are a tremendous set of applications we can attack, particularly in the specialty chemical bioprocess, as it were, that we can help you model more efficiently and get better insights into your simulations. That again, more value per minute simulated and more value per man hour invested into the code. With that, I'm going to open the floor to any questions. If people have questions, please ask them through the chat. If not, that's no problem. You can reach out to me directly after the fact. But now is your chance. Feel free to ask. And if there is nothing asked, that's fine. But yeah, please fire away and ask any questions that might be out there. I'll give folks a few minutes to respond. Well, this is what people might be thinking. I'll just kind of reemphasize this. And again, chat here. And, ask any questions here. I'll invite people to do that under the chat option. And just kind of checking in on this. This guy's running just as I promised, right? He's moving through space and time. Now this is again, our single-use bioreactor, 2,000 liters, with the glucose control. Not much to see yet, so maybe I'll go to the code and do a quick write so I can see what kind of data I have coming out of the system. But this is what we got. We got a question, I think, yet. Can you a little more? Oh, not yes. Great question, Hawk. Thanks for that. Okay, I breezed through this, and this is a topic that deserves a little more discussion. But this is an important point, and admittedly, it's a very kind of computer science point. But it comes down to doing math on a computer. Take a look at this here. If I have a cell density that's typically measured on the order of 10 to the 9, right, cells per milliliter. My growth rates are going to be on the order of like 10 to the 3, as it were, cells per milliliter per second. But my time pip is 10 to the minus 3. Most computers, especially if using single precision, can't add that, okay? Like 10 to the 9 plus 1, they'll see as 10 to the 9. In fact, if you ever want to kind of impress someone with Excel, watch this. If I go to Excel and I go 1, and I go to minus 0.1, I go to 0.9, 0.8, 0.7, I don't get 0. That's because like the computer can't do math super efficiently when it's taking small differences. And so to eliminate this effect, we do math with numbers much, much closer to 1. That is, we divide the cell density by the initial value. We divide the glucose concentration by its initial value, as it were. We still operate in real terms when reporting data. We do all our math and physics behind the scenes with numbers that are pretty close to 1, as opposed to numbers that are 10 to the 9 and 10 to the minus 6. So again, non-dimensionalization is not specific to this particular, to MSTAR, not unique to us, but it's a common approach used to make problems a bit more tractable. And again, if folks want to see that in action, I'd be happy to send them the model. But that's kind of the key point, is to minimize some of these rounding errors, we do a non-dimensionalization. Great question. Anything else? Any other kind of muddiest points or things that weren't particularly clear? There might have been a few. I have a habit of speaking quickly, even for English speakers. And so, are there any questions that folks have? I'd be more than happy to take those on as well, or things that were unclear. Absolutely, you can couple. Yes, great question. You're correct in both regards. Yes, sometimes we have heat transfer in the jacket of the single-use bioreactors, and we CAN model that in MSTAR. In fact, we have some good literature. I wrote a paper not long ago that spoke about this in this the heat transfer physics. So yeah, this is a paper that I wrote that talked about convective heat transfer in both agitated vessels and other sort of piping systems, as it were, like flow through pipe or flow over coils. So yes, we can incorporate heat transfer. We've had very good success in linking predicted versus measured Nusselt numbers. It's not anything I included in this model, but it's absolutely something we include in the physics. And it's a next step in these models, and it's not a hard next step because the physics are already ready to go inside the code. Great question. That's the physics we can handle very well. Thank you for that. Han In Su. Wait, is it Han In Su? Yeah. If you wait long enough, I'll tell you my Korean name. It is Minam, beautiful man, obviously. No, I'm just kidding. But okay. How many lattices are used in simulation for several days of cultivation? Yes, a great question. So in this particular simulation here, which is one I modeled for several days, this had about 5.6 million. Okay. So admittedly, I'm skinny on resolution at 150. Maybe I'd want to go to 180 to get a better description of EDR, but I'm really trying to keep my lattice size small to run quickly. But yeah, 5 million is still pretty good. So if I go to the simulation here and kind of chime in to see what we got going on, let me kind of show this guy evolving and go to my surface with edges. Like, it's not a terrible resolution, right? Like, I've still got a pretty decent resolution to resolve the power number in EDR, but I do want to be mindful to keep that resolution modest in order to keep the simulation run times as low as possible. But yeah, good question there. Great question. We've got time for 1 or 2 more questions if anybody has any. If not, that's no problem. These have been excellent questions so far. And again, should folks want to see these models or want access to these models, I'm more than happy to send them to you. We got one more question coming in. Wonder what hardware? Oh, that was an A6000 GPU. It was a workstation. I need to double check. I don't know if I have it here. It was a single GPU. Maybe it was an A5500. It was one of these guys. It was either an A6000, not a camera. Yeah, it was either an A6000, which is, a few $1,000, or it might have been, I need to remember, or it might have been an A5000. I need to double check, but it was one of these GPUs. It might have been A55, but it was a single GPU I think it was a 5500. I'm pretty sure this was it. I think it was a 5500, but it was one GPU in a workstation. So yeah, nothing exorbitant. Great question. Yes, this is correct. This is correct, Kenneth. And again, I'd be happy to send you the models that achieve that, as it were. Now this one here, this is this guy's cranking along, but I'd be happy to send those models and show some of that scaling performance. Thank you, Navraj. How do you define the model and what was the last week? Okay, great question. So in this case here, when I'm adding glucose and glutamine, I have a cylinder representing the bolus addition. So I didn't model the inlet explicitly. I instead defined a feed boundary condition here that's leading to the addition of glucose and glutamine in that region of the cell. One thing I did not include in this model was a free surface and volume changes. We can do that. That's not a problem. But for simplicity and validation, I assumed that we had a fixed volume, which was appropriate for this model, which led to this kind of just source addition. But yeah, in a more sophisticated model, I could model the free surface changes and the jets coming explicitly. Within the model, I had a child volume with just a specified addition rate that was informed by the glucose feed rate. Where does the glucose feed rate come from? It comes out of the PID controller. So it's all embedded in play. A great question, Navraj. Guys, looks like we're at time. Please reach out to me or CAT-IT. Thank you, CAT-IT directly. Thank you so much for organizing this talk and coming here today. Appreciate your great questions. Show me you understood, and reach out with more. And I'm happy to send any data, models, papers you need to demonstrate how well this works. Thank you, guys. I appreciate your time. Have a great remainder of your day. Thank you again for coming. Bye-bye, guys.